So last video, or a couple videos ago, I talked about line integrals, but it was specifically for scalar fields. Now let's recall what a line integral is. So say we have some surface, so this right over here is my surface. Looks kind of like a sheet, right? And let's say that I take some kind of path, okay? Now I'm essentially, when I'm doing a line integral for a scalar field, all I'm doing is I'm just accumulating the function. So right over here, for a small step that I take the height of this function at that point, and I get the area of that one strip, and I keep doing that, right? As I move along my path, I'm going to essentially accumulate an area based off of the height of the surface at that specific path point. Okay, so for every point on this path, it's going to be associated with a height on our surface, and we're just going to sum it all up, right? Hence why, if you do the line integral formula, the short version for the scalar, thing is the line integral for our curve, right? That's going to be equal to essentially our surface evaluated at that specific point, so at that specific xy value, and then it's going to be multiplied by a tiny step in whatever path we take, which I'm just going to call it ds. So ds is a tiny step that we take. And so just multiplying these two things together and summing it all up will give me the total accumulation underneath the surface. Recall that a vector field is essentially some kind of function, all right, which takes in a single point. So let's say if I have a function, I'm just going to call it f again, right? It's going to take in a single point, a single xy point, and what it's going to do is it's going to output a vector, and it's going to do that for every xy point in this case. So, if I were at this point right over here, at this xy coordinate, let's say this was 0, 2, right? Then I would have a vector going up associated with that. So given the initial xy value, I get a vector of, let's say, 2 units up, right? 2 units up. Or you can say that this is a vector that has a 0 component in the x direction, but it's going 2 units up in the y direction, right? Or if you were to look at this point, this vector would be associated with it. So in short, we have essentially a function that takes in a point and it outputs a vector. Now, this function right over here can be written or in like a more general format, okay? So we know that vectors, they have an x component in 2 dimensions and they have a y component. So I'm just going to say that this gives a vector, right? This is going to be some function where, the x component of this vector is going to be determined by some function of our inputs, and the y component of this vector is also going to be determined by some function of our inputs. So let me give you an example of this. Let's say if we have f of x, comma y. So given an x coordinate and a y coordinate, let's say that our vector field formula is, xy plus y, and then let's say this is xy. So you can see how, given any x and y value, I'm going to have a vector associated with it. And so this p of x comma y just represents a function that determines the x component of this vector. And this xy right over here is the function q of x comma y that determines, the y component of this vector. I think you can also write it as like p of x comma y I plus, and you can use like the ij notation like that. But I'll just write it like this because we're actually going to get into dot products, which is going to be pretty cool. Now, if we want to consider line integrals in a vector field, we're going to have to reframe our problem a little bit. It's not just accumulating, that area underneath the surface. Our objective in this video is, for a given path that we take, we want to find out the total work that this vector field does from point A to point B, all right, traveling along here. So you see how when I start at this coordinate, -2, -5.2, right, there's going to be a vector associated with that. And it's going to be doing work given, our tiny displacement, right? We're moving along this path. And this vector field is going to be, pushing us around a little bit, and there's going to be work done for every point that we travel along this path. And so our problem is that, how do we calculate this work? And for that, you might need a little bit of physics review. So let's talk about work in physics. work is equal to force times displacement times the cosine of the angle between those two things. So let me give you an example. Let's say if I have a box on a surface. And let's say that my force vector, or let's say that the box moved a displacement of 5 meters. So the box is moving to the right. And let's say that we, as the little human we are, we decide to push the box with a force of 6 newtons. But this force is going to be at an angle. Let's say a 30-degree angle. So you can see how we want to measure the work done by this human. Now, some of the work is going to go along the direction of our displacement. So you can imagine that, our force vector has like an x component, and it also has a y component, right? So some force gets directed along the same direction as our displacement, and some force is kind of just useless, right? Because we're trying to push the box to the right. We're not trying to push it up, right? So we really only care about the force in the x direction. And so how do we get the force in the x direction? Well, we can use cosine, right? So let's actually find out cosine of this angle. So cosine of this angle, 30, is going to be equal to, the adjacent side divided by the hypotenuse. And so we get that the force in the x direction is equal to our original force times cosine of the angle. Hence why we have this cosine in this work formula, right? This f cosine of theta part ensures that whatever force you're looking at, it's in the same direction as our displacement, right? It's like kind of like a similarity measure, right? How much of this force vector is actually going into the direction of our displacement? But what is this equal to? And this is so familiar because recall that, well, this is just the dot product. Recall the dot product formula, right? If you have A dot B, that's going to be equal to the magnitude of A times the magnitude of B times cosine of the angle. And this is great, right? On this path, right? So as we travel along this path, to find out the amount of work this vector field does based on this path, what we can do is for a tiny little displacement, which I'm going to call dr, right? I'm going to also calculate the vector field at that specific point. So this is going to be the vector field at that specific point. And I just take the dot product between the two to calculate work, right? Because we said work is the dot product of, whatever, you can think about this as a force vector field. So whatever force that we have at that specific point dotted with whatever displacement, whatever tiny displacement we have at that point. And we just sum it all up for all points along the path. So we have a general formula for vector line integrals in vector fields. So I can say that the line integral for our vector field is going to be essentially our function evaluated at that specific, little point that we're on. And then we're going to take the dot product of that with our little path. And we just sum it all up for all points along our curve. And so this right over here is the general formula for the line integral for vector fields. Now, let's try to make it simpler to actually calculate. So this is kind of like the conceptual formula, but we need to turn it into a form that we can actually calculate. Because right now we have some weird vector thingy here, and then we have some dr. What even is, dr? Well, take a look at this. Let's say that I'm on this point right over here. And let's say that this tiny change right over here is dr. Notice how all I'm doing for dr is I'm going a tiny bit in the x direction and a tiny bit in the y direction. And recall that dr is a displacement vector, right? Dr is also a vector, right? That's why we were able to take this dot product, right? It's the dot product between the vector from the vector field and the vector from the path displacement that we take. And so I can say that dr is essentially equal to, well, it's a tiny change in the x direction and a tiny change in the y direction. Okay? And so that's why you might see this line integral formula written as another form. So take a look at this. What's f of x comma y? Well, we said that's p of x comma y and then q of x comma y. And we also know that dr, well, what's dr? Dr is a tiny change in x, essentially, and a tiny change in y. And so if I take the dot product between these two things, well, I am just going to get, well, this line integral. We're still on the same curve, but now this is going to be p of x comma y dx, right? Remember the dot product things, you kind of multiply them, and then plus, and then you multiply these two, so q of x comma y dy. And so you might see the formula written out like this, or in even simpler terms, p, this is the line integral of p dx plus q dy. And when we eventually go into Green's theorem, you're going to be converting this into a much simpler form to calculate. So, elephant in the room, how do we parameterize dr? And it's going to be the same thing that we've dealt with in scalar line integrals, okay? So, notice how the curve, it's essentially just, you have a point and it has x coordinate and a y coordinate. And so I can say that I'm going to parameterize this function r in terms of a variable t once again. And so t is going to have an x component, right? So you can think about it as having an x component, x of t, right? So there's the component x of t and y of t, right? So for every, you can think about this function as saying for every point along this curve, well, then, this point right over here or this point right over here, right? This r function is going to be determining what this curve even is in the first place. And it's going to be essentially a function of x and y. But we parameterize it into t, so that it's just one variable. And so therefore, if we want to find out the value of dr, right? So now that we parameterized this r function in terms of t, dr is just going to be equal to, well, think back to the chain rule. It's going to be equal to dr over dt times dt, right? It's like what you've done in calculus, right? dy dx is equal to f prime of x, right? And so if you quote unquote multiply both sides by dx, you get that the slope times that tiny change in x gives you a tiny change in y. That's exactly the same case we're having with our t's and r's, right? A tiny change in t causes a tiny change in r, and so dr is just going to be those changes multiplied together, okay? And so we know what dr is equal to. Dr is equal to the rate at which r changes with t, or I can just write that as r prime of t times dt, right? And as for our original function, well, what about this x and this y? I want to turn it into one variable t. Well, we already turned it into one variable t. Because we parameterized the curve, we can give our vector field the exact same parameterization too. And so this just becomes f of x of t. So this becomes f of x of t. So instead of x right over here, well, we have x of t and comma y of t. And so this is our final formula that we can actually use to solve these annoying line integral problems. Let's evaluate this line integral where this is our original vector field and this is the curve. It's already parameterized for us, and these are the bounds. Let's do this. So we know that the bounds are going to be ranging from 1 to 0. And so we see that, well, you can think about this right over here as our parameterization, where our x value is essentially t, and we parameterize y as t squared, okay? And so let's calculate this last part first. What's r prime of t? R prime of t is just going to be, well, what's the derivative of t? 1. What's the derivative of t squared? That's just 2t. And all of this is, recall, with respect to t, right? That's what we're integrating for. And then our original sort of function here, it was x squared y minus y, and then xy. But recall that instead of x turns into t, and y turns into t squared. And so we essentially, instead of x squared, well, we have t squared. That's easy. Minus y, well, y is also t squared. So that's very nice, right? That's just going to be 0. And then x times y, well, t times t squared, that's just going to be t to the third power. Let's do the dot product. This is going to be the integral from, whoops. Sorry about that. All right, so this is going to be the integral. And then, so if we do the dot product, this is just going to be, well, these parts kind of, 0 times 1 is just 0. So you're just going to get 2t to the fourth dt. And now we can solve. This is just going to be the reverse power rule. And so once we evaluate it from these bounds right over here, we're just going to get 2/5, right? Because 1 to the 5th power is just going to be, 1, and you just get 2/5. And so that is the total work that this vector field does given our little curve that we traveled on.